Hello everyone. I will start. It's really a pleasure to be here for the second course and to see so many people. So last time I started off really enthusiastically and I didn't say anything, but now I just want to say I like to keep it very informal. If you have any questions, please just ask, and I think it's always nice to have a kind of discussion during the lecture. So what I promised, we discussed last time that we have this phase transition and we want to prove this phase transition, that it exists. And what we did is we saw this model is related to another model, and we're first going to prove a phase transition in this other model and then teleport the result back to the original model. And finally, as a sort of bonus, we're going to understand some extra behaviors of this phase transition. So what I'm going to do this time is I'm just going to quickly recall the fundamental objects that relates the two models. Then I'm going to completely forget about the xy model and completely focus on the other model, which is the height function. Okay? So what we did last time was the following. We had a finite graph which resembled a large portion of the plane. Okay, you can have a different opinion about what's large, but this is pretty large, I think. And we take a Poisson process. So actually what do? We look at a collection of Poisson random variables which are indexed by the directed edges. And we kind of think of this Poisson random variable as telling us how many directed edges of each type there are. So there can be 2 or 0 or 1. They can be in both directions at the same time. And what we saw was that the fundamental object that we look at was kind of this measure beta, mu beta. So mu means independent Poisson random variables for the directed edges with intensity beta. So it's IID Poisson random variables with intensity beta on the directed edges. And the partition function corresponded to the event that, that n is sourceless. So what is this event? So this is the event that at each vertex the net degree of n is 0. And the net degree is just the number of outgoing and incoming vertices. And what we realized was that if we have a configuration n which satisfies this constraint, so here it's clearly not the case, but let's try to complete the picture. Does this work? Yeah. No. So, for example, in this configuration, the number of incoming and outgoing arrows is the same at each vertex. And in this case, we can assign to each phase the winding number. So, for example, here it's 1, 1, 1, 0. And if you go between two phases, then the height difference is exactly equal to the number of edges you cross in one direction minus other direction. And because of this constraint, this is consistent. Okay. And what we also noticed was that beta, this is the inverse temperature of the xy model. So when the xy model is at a low temperature, it means that beta is very large. And it means that a priori, when you don't look at this event, but just at this measure, there are a lot of Poisson edges, right? Because this is a Poisson random variable with a very high parameter, which kind of means that this height function, you can think about it as being quite flexible. On the other hand, when t is very large, that means that beta is very small. It means that in this measure, typically there are very few directed edges. And on the level of the height function, it means that the height function is very stiff. And well, what we're approximately going to prove today is that, well, it's known that if beta is very small, so the height function is very stiff, then the height function is flat. But what we're going to prove is that when beta is very large, the height function is not flat, so that the height function fluctuates. Okay. And to do this, I will now write down the main theorem. So in fact, for the graph, I'm going to cheat a bit. Well, actually, I'm going to cheat in quite an essential way. But the graph that we work on is going to be the hexagonal lattice. Beta is going to be some fixed parameter. But in the end, we're going to take beta very small. So in fact, the beta is going to be the inverse beta here, right? Because you have this Fourier transform, it has this associated, temperature inversion, and I just want to write beta here. I'm going to consider domains of this graph. So domain is a finite subset of V. And I'm going to consider a probability measure on height functions. And okay, here I define them on the faces, but here I want to define them on the vertices of the graph. So H is going to be a random integer valued function on the vertices. And its law is given by the following rule. So mu in lambda. So the probability that H is equal to a certain function zeta. This is by definition equal to 1 over the partition function in lambda times the indicator that the support of zeta is contained in lambda times e to the minus beta sum over edges which are incident to lambda times the height difference squared. Okay. So what I'm doing is the following. I look at height functions which are 0 outside of lambda. So this is like imposing 0 boundary conditions outside of lambda. And then the probability of a height function is e to the minus beta times the sum over the height differences squared. So notice that we define this for integer valued functions. If we would define this for continuous functions and we took this as a density with respect to the back measure, we would have the Gaussian free field. But crucially, we're conditioning the Gaussian free field to take integer values. And this really fundamentally changes the behavior of the model. So this is not the GFF. Okay. So I will now write down the main theorem of today, and this is really the sort of the, well, not the only goal, but the main goal of today, which is that if beta is smaller than the logarithm of 2, then the limit as lambda approaches the entire thing of mu lambda of the variance of a vertex equals infinity. Okay? So what this means is that, okay, I fix one vertex, it doesn't really matter which one. And then I define this measure in a finite domain. And in a finite domain, I can look at the variance of the height. Now, of course, my system is completely invariant under flips, so the variance is just the expectation of the height squared. And I assert that if I take this further away from the origin, then this variance tends to infinity. And I want to stress that at this point, it's completely a qualitative result. So for example, if this is the GFF, then we also know how fast this square goes to infinity, the expectation, because we know that the variance in fact blows up logarithmically in the distance from x to the boundary of the domain. And in fact, later we shall see that the same holds true for the integer valued function. So if you know that the variance is infinite, then later you can do a sort of renormalization procedure to see that it must go to infinity at least logarithmically fast. It's only a lower bound. But that's not what we're going to do today. Today is only the focus on, on this theorem, which is qualitative. So what I want to stress is that in this paper I rely a lot on the results of Sheffield, which is 2005. So it's his PhD thesis called Random Surfaces. And in this PhD thesis, he studies height functions, not just in 2 dimensions, but really in any dimension. And he studies these height functions using percolation theory. And it is essentially the first work in which percolation theory is systematically used to study height functions. So he used certain ideas, well, that we're going to discuss later, about height functions. So this is percolation and also height functions. So when I wrote this paper, in fact, I was relying a lot on this work, which contains a number of extremely deep results. And then 2 years after writing this, I was in a collaboration with Sébastien Ott, and Sébastien realized that, in fact, I mean, we shall later see that we can do percolation because we have an FKG inequality. But he realized, in fact, that there also exists an FKG inequality for an other object, which we're going to see today. And this really allows, like, really a simplification of this proof. Which is due to an FKG inequality, which we called absolute value FKG. So this result, it wasn't really necessary to get this result, but it hugely simplifies the analysis. And this absolute value FKG plays an essential role later on in the analysis when you want to do this renormalization. So it's a qualitative result here, but when you want to quantify it, this absolute value FKG becomes very important. Okay? So today I will not present any of the results here because they take too much time to explain, and rather I would like to explain the simplified argument. So what we're going to do is we're first going to develop, okay, I mean, I think for some people it's going to be more interesting than for others, but the first thing is we're going to do percolation theory. So I want to discuss a number of results, including the one that we did at the end of last lecture. And then I want to prove 2 steps. So the proof of this theorem goes in kind of 2 steps. And okay, I'm gonna prove them in the reverse order. So what is step 1 of the proof? It's the following: assume that the theorem is false. So okay, we fix a beta and then okay, it doesn't blow up. Then these measures converge to some limit mu, in the local convergence topology. And mu, right? So this is as lambda becomes bigger and bigger. And mu is, is ergodic. Satisfies FKG inequality. And has flip symmetry. Okay, so what does it mean to converge in the local local convergence topology? It means I have my domain, but I say that I restrict my attention to a finite box, and as I take my domain, my boundary conditions further away, what I'm going to see in this box is going to converge. This is the local convergence topology. And if you take this limit, actually we're going to prove that it's the same limit no matter how you take this thing to infinity. And because of that, this limit is going to have all the symmetries of the graph. Right? So this limit, for example, it's going to be symmetric on their flips, and you can rotate by 2 pi over 3. So it's a very symmetric measure, and it has these other properties, which I will introduce in a second. And then in step 2, so this is kind of the second step of the proof. We introduce a new thing which is called symmetry breaking. To deduce the following result, which is maybe a bit counterintuitive. So in mu, we have the following stochastic domination. If we take h and we subtract 1/2, then this stochastically dominates minus h, I think it should be plus 1/2. Okay? So this is at a fixed vertex x. So it means I fix a vertex x, I'm just going to look at what happens there. Right? I have this, I've constructed this measure mu, which I got by taking my boundary conditions further and further away. And now what I see is that I get this stochastic domination. Now, if you look at, if you rearrange this a little bit, what you see is that, okay, we're just going to simplify. So it's 2hx. Oh, okay, it may also be horribly wrong. I don't know. No, wait. Okay. So actually you have the flip symmetry, right? So you know that everything is flip symmetric. So if you have this, then you also have hx minus 1/2 is greater or equal than hx minus 1/2. Okay, I think maybe there should be a minus here. Then you get a plus. Okay. So this is clearly a contradiction, right? This is not true. And this is actually a contradiction which we're going to derive. Okay? So we somehow, I mean, of course, we assume that the theorem is false. We construct this limit which satisfies a bunch of properties. And then we get a stochastic domination which is clearly absurd. Right? I mean, if you have a measure on R and you shift it down, of course it's going down, it's not going up. Okay? Yeah. So in the first part, we're just going to do a bit of percolation theory. That's the.
Yeah, I was wondering the measure that you introduced.
Yeah.
Is it obvious that it's the same as the one you're considering with the Poisson?
Yes,
Yeah.
that's a very good question. Of course, there are two differences between the two models. The first is the graph because it's the hexagonal lattice, and secondly, the potential is in fact not exactly the same. So it's a slightly different potential. Actually, I took this potential simply because it's a little bit easier to write down the formulas. But really, the potential doesn't play at all an important part in the proof. So you can really think about the same potential as there. And then later, in the next lecture, we will see how to get rid of this, the fact that it's the hexagonal lattice. So like there are two differences, and one, like this potential is a small difference, and this graph is like a more substantial difference.
Where do you use the beta less than log 2 in your proof? At which step?
Yeah, it's at the symmetry breaking. Okay. So in fact, step 2, like this step 1 is always true. If, I mean, okay, here I say assume the theorem is false, but in fact we could also say just assume that the variance is finite. If the variance is finite, then this whole step 1 holds true. So this is just, yeah, you just assume that you're localized, you assume that this is finite, right? So this is called delocalization. So if the model is localized, then we can make sense of this limit. This is all perfectly fine. And then to get the contradiction, we assume that it's localized, and then we use this symmetry breaking. And that's where we use the requirement. Because once again, we know that for beta very large, the model is very stiff. You want to stay at the same level, and even the minimal deviation costs you a lot. And then you can prove that you're localized. So if the variance is infinite, then by definition you're localized. And this is in the end what we're trying to prove. Okay, so
Just one simple question. Why is that a definition for mu lambda? Because the values that can take h, h takes value in the infinite set z. So that's
here?
no, like the definition of the measure.
Yes.
How do you shift it so that it's translated? Like it's written, it's translation invariance.
Well, we say that the support, it's just a way of notation, but the support is included in lambda. So it's really like you fix 0 boundary conditions. But later we shall also see how you can encode different boundary conditions. Yeah, it's a countable set, of course, the support, but that's fine. Like the sum is finite, so the normalization is okay. Okay. Okay, we already defined the FKG inequality last time. Oh, so it's the FKG. So it's for time Castellijn Ginebra. And we take a partially ordered set. And then we say that mu has the FKG inequality, or it has FKG, if mu of FG is at least mu of F times mu of G for all Fg from omega to R, which are bounded and increasing. So of course, increasing is always with respect to the partial order on our poset. And okay, we say also an event E is increasing if and only if its indicator is increasing. Okay, so this is all very abstract, but in practice, I mean, in practice what happens is that this is often just R to some index set, right? And then you just take the partial order on functions on I. So for example, yeah, you can have measures which are supported on functions which take value 0, 1, and then it's often called percolation. But like for example here, we take functions which are supported on integer valued functions. Okay, and the first kind of trivial observation is that you can use FKG inequality to see that certain measures are stochastically dominating other measures. Right, so we say that mu is stochastically dominated by nu, and we write it like this. Right, so now we consider two measures on the same partially ordered set. If mu of f is always below nu of f for all f increasing. Okay? So for example, if mu satisfies FKG and E is increasing, then mu is stochastically dominated by mu conditioned on the event E. So why is this true? Well, it's actually very simple. The definition of the conditional measure, we're just inserting the indicator of E. This is an increasing function. Now, if we want to see if things stochastically dominate each other, we're just comparing how it acts on increasing functions. So now if we fix an increasing function f, we also have an increasing function which is the indicator of E. And then the FKG inequality will tell us that we have this stochastic domination. Okay, so yeah, you can think about the FKG inequality as this, but it's really very close to saying something about stochastic domination. And of course, we're also going to use that there later. So I think many people know that the first time that this inequality was proved was for percolation. So for example, if mu is a measure on Ri, such that mu is in fact a product of separate measures on R, then mu has FKG. So this is called the Harris inequality. So yeah, this is what I want to do is to give a quick proof of this Harris inequality, which is maybe a little bit different than okay, what is presented in a normal course. And this is called the Tower property that we're going to use. And the Tower property will be useful to us later. So we're going to apply it now in a kind of trivial case, but later we're going to apply it in a non-trivial case. And okay, I think this Tower property appeared for the first time in the paper of Sebastian Ott and myself. But it's really quite a simple concept. So we start with two posets. We start with mu a probability measure on omega with fkg. Okay, what we're going to do is the following. We're first going to consider a probability measure on omega, but then we're going to consider for each point in omega a probability measure on omega tilde. And you can kind of think about this as a conditional probability, right? So to sample from omega tilde, first what you do is you sample something from omega, and this gives you a conditional probability that allows you to sample from omega tilde. Okay, so you start with a probability measure on omega, you sample your little omega, you put it in kappa omega, it allows you to sample from omega tilde. So both measures have fkg, but we need one more relation. We want that this map is increasing. So of course for it to be increasing we need an ordering on both sides. Omega belongs to a partially ordered set. Yeah?
Sorry, is x omega there for all x?
Yes, thank you. So here we have the partial ordering in this set, and here we just have the partial ordering which comes from stochastic domination. So if we have this, then the resulting measure on omega tilde has fkg. Right? So how do we prove this? We define mu to be this resulting measure. And of course, to see that this has the fkg inequality, we need to show that, well, if we plug in two increasing functions on omega tilde, then we're positively associated. Right? So we want to prove that if I put in two increasing functions, then this is going to be bigger than, well, if I put them separately into mu. So by definition of mu, this is just equal to, we integrate with respect to omega, and then we take kappa omega f of g. So this is really just a definition of nu, right? Because for nu, we first sample from omega, condition on that we sample there, and that's just this measure. So now here, we have an fkg inequality, right? We use this fkg inequality. So this is bigger than d mu of omega of kappa omega f kappa omega of g. But now we can ask, what is this? This is actually an increasing function of omega. By my definition of, well, I have here this stochastic ordering. So if I increase omega, this thing is going to be bigger. And now we can use the fkg inequality for omega, for mu. Right? So this is fkg for, omega. And now we use d mu. So now it's going to be kappa omega f d mu omega kappa omega of g. And this is fkg for omega. Okay? So it may seem a little bit tautological, but it's really just a sort of chain rule or a tower rule if you want. So now we prove another lemma. If mu and nu have FKG, then, so they can be defined on different spaces, then the product of the two measures also has FKG. So maybe they are defined on omega 1 and omega 2. So how do we use this theorem? Well, it's actually quite simple. For mu, we just take mu. And what is the conditional sample of the whole sample conditional on the first sample? Right? K kappa of omega. This is just going to be the Dirac delta at omega times nu. So first we sample something from mu. Well, that gives us the outcome of the first element. Then we just sample independently the second element. Now, okay, mu has FKG by assumption. Since nu has FKG, okay, if we just take a product with the Dirac delta, clearly it's still going to have FKG. And, well, it's increasing because we're just increasing the Dirac delta. And then finally, if omega is totally ordered, then any measure has FKG. Okay? So for example, if I look at any measure on R, and I take two increasing functions on R, then the expectation of the product of those functions is always going to be bigger than the separate expectations. So I will leave that as an exercise. Okay, so I mean, for the Harris inequality, we're just using two inputs, namely for totally ordered, it's trivial, and then we have this product rule. But this product rule is actually a corollary of this more general Tower property. So maybe it's good to check who in this room has already seen the FKG inequality. Okay, that's good to know. There's a more general way of establishing the FKG inequality, and that is through the FKG lattice condition. So I will first explain the result, but I'm not going to do the entire proof. So in this case, we don't look at a partially ordered set, but rather we're going to consider distributive lattices because they have slightly nicer properties. And for simplicity, let us just constrain ourselves to countable distributive lattices. So in practice, what that means is just that this is going to be R, okay, a subset of R to some index set. This is just a natural partial ordering, and here we're just taking the pointwise minimum and the pointwise maximum. Okay. So now we can define functions in omega. So we consider a function x on omega, which is kind of a weight function, and it tells us how likely every configuration is. And now we define the mu of a certain omega as 1 over the partition function of x of omega. Right, so it's really just the weight function. now there's a definition, which is the FKG lattice condition. So X has FKG lattice condition if X of omega nu, X omega nu, oh my god, the choice of letters is terrible. Okay. So what we say is if we take any two elements in our distributive lattice, then it has a higher weight to consider the maximum of the two and the minimum of the two in this distributive lattice than to consider the original ones. So there's a very general theorem, which is why it's called the FKG inequality. Namely, if you satisfy the FKG lattice condition, then the measure has FKG. So I don't want to give a proof, but basically what it's saying is that the model just prefers to be sort of big together or small together rather than to be big somewhere and small somewhere else and then the other way around. Right? So one thing which is nice about the FKG lattice condition is that if I have a function, if I have two functions which satisfy the FKG lattice condition, then clearly the product also satisfies the FKG lattice condition. So often what you can do is you can kind of define a model in which the weight of each configuration is like a product of different weights. You prove the FKG lattice condition separately for each weight. And yeah, then you get it automatically. And then later you can also use this Tower property to get FKG inequality for more complicated measures. So I think the simplest model that we all know is the Ising model. And of course, the Ising model has the FKG lattice condition. But I want to introduce not directly the Ising model, but first directly its coupling with another model. Okay, so this is called the Fortuyn-Castellijn coupling. So G is going to be a finite simple graph. And we also fix a family of coupling constants which are all going to be non-negative and which are associated with the edges. And mu on G with coupling constants J is going to be the probability measure on this pair. Which is defined as follows. The probability of the event sigma omega equal to sigma tilde omega tilde is going to be 1 over partition. So first we have a consistency relation, which I'll explain in a second. And then we have some other factors. Okay? So what does this mean? We're sampling a configuration on both sides and edges where we have the spins on the sides and we have a percolation configuration on the edges. So, yeah, we consider simultaneously a configuration of pluses and minuses on the vertices, and yeah, a percolation configuration on the edges where some of the edges are open and where some of them are closed. And we say sigma tilde is consistent with omega tilde if sigma is constant on each open edge. Okay, so in this case it's consistent, and we see of course that the pluses and the minuses are not connected, because if they would be connected there would have to be some edge connecting a plus to a minus. Okay. What I mean by this term is that, yeah, I have this kind of shorthand notation, which is that if a and b are functions from x to c, then a to the power b, this is just the product of x in x of ax, bx. Okay? So omega is a percolation configuration, so it means that if omega is open, then we take one of the factors here, and if it's closed, we take one of the factors there. Okay? So I mean, e to the j minus e to the minus j to the power omega, this is just equal to product of xy in omega of e to the j xy minus e to the minus j xy. Okay? So I will clarify this in a second. So now what you can do is you can look at the two marginals of this measure. You can integrate out sigma and you can integrate out omega. Okay, so let's first integrate out omega. So we fix sigma and we look, okay, what is the weight of this sigma under this measure, right? So we're gonna find all the omegas, sum over all those weights, and then we get just a number. So now the first key observation is that in principle we have this consistency condition. So what this means is that if we fix, so we fix sigma. If we fix sigma like this, we know that if this edge is open, then well, we're kind of dead, right? I mean, the contribution is going to be 0 because of this factor. And if the two endpoints are the same, then of course this thing doesn't really care. So to calculate this number, we can forget about this term, but we can only, for each edge, we have to look, can we put it or not? If we can put it, we have two options. And if we can't put it, we only have one option, we can't put it. So if sigma x equals sigma y, then the edge can be both open and closed. And in this product we get both weights. So we get both this one and this one. Well, if we sum them, the minus j disappears and we just get the plus j. So we get e to the j xy. And otherwise, otherwise then it has to be closed, right? So edge must be closed. It must be closed because of this, this vector. If it's open, you just get a contribution of 0. And if it's closed, then, well, we only have this term, so it's e to the minus j xy. Okay? So what this tells us is that mu of sigma equal to some sigma tilde. This is going to be e to the j to the omega. Oh, okay, that doesn't make any sense. Product, so it's proportional. Yeah, it's 1 over z product xy e to the j sigma x sigma y. And that's it, right? So if the two are the same, then the product is of course equal to 1. And then we get e to the j. If they are different, then their product is minus 1, and we get minus j. Okay? So if we forget about the omega structure, we retrieve this object. This is the Ising model. And what is important to observe is that if I forget for a second about this product, it's easy to check that this vector, I mean, this is a function which maps sigma to some real number. Right? If I put in sigma, I can just calculate this. And this term has the FKG inequality. It has this FKG lattice condition. Right? Because what I need to check, if I say, okay, this, I can say this is, I define this as x. And then I can just check this. I mean, what I'm saying is that if both my edges are open, I will get e to the j. If both are closed, I also get e to the j. But then if one is open and the other closed, I get e to the minus j. Right, so you're always doing better plugging in the pointwise minimum and the pointwise maximum than to put in your original configurations. And then it's simple because we're just taking a product, but this FKG lattice condition is stable under taking a product. So this has FKG. Okay. So now what you can do is you can ask the same question. I fix omega and we integrate out sigma. So here we did the first one. So now we ask, what about mu of the event omega is equal to omega tilde? So in fact, now it's kind of simple because, well, we need to sum over sigma, but sigma only appears here, right? So there's no sigma in this weight over here. So the only thing that we're counting is how many configurations are there which are consistent, right? We fixed our percolation, but we don't see what's here, and we're just counting. So this is equal to 1 over z times the number of configurations, but this is just 2 times to the power k of omega. And this is the number of connected components. And then we have the same factor as before. So it's e to the j minus e to the minus j omega e to the minus j 1 minus omega. Okay. And in fact, what you can verify, I mean, of course, if a factor depends only on one of the sort of i's, right? So you have a factor which only depends on one of the indices, then this factor automatically satisfies the FKG lattice condition. In fact, you will always have equality here, right? There's really nothing going on. So for all those factors, it's completely trivial that you satisfy FKG lattice. But for this factor, you can in fact also prove that it satisfies FKG lattice. So this you can do, for example, by checking the Holly criterion. And it's really something about counting connected components. You need to see that if you take the maximum and the minimum, for the sum you have more connected components than if you look at the configurations separately. Okay, I think we're going to take a 5-minute break until 3:03, and then we continue. Thank you. So this FKG inequality is really somehow at the core of all this work, and somehow manipulating this in various ways is really sort of it opens up the entire problem. So what we just did is that we defined this measure mu on both spins and edges, and we proved that in fact both marginals have FKG inequality. So this is maybe quite a remarkable thing where you have a measure on a product space which doesn't have such nice properties, but the two marginals do have it. And in fact, it allows us to write down certain relations between the spin model in terms of the percolation model. So for example, what we saw is that if I fix the percolation configuration, then I'm choosing uniformly at random a way to arrange the spins in such that neighbors have the same spin, right? So for each connected component, I'm just flipping a fair coin. And vice versa, if I fix sigma, I'm just doing a percolation procedure. But if I take now, for example, if I take A a subset of V, and I consider the product of the spins in A, then this is equal to the probability of the event Fa. And what is this? This is each connected component of omega intersects A an even number of times. So why is this the case? Well, suppose I see my configuration, my percolation configuration, and I want to calculate the conditional expectation of this quantity here, right? I take a product over spins. Now, suppose that A, okay, now we're going to take the red. If A is a set like this, and this is my percolation configuration, then clearly the expectation of A is going to be 0, because this connected component intersects A exactly once. So if we flip the outcome of the coin on this connected component, we're really flipping the value of this random variable. Right? So if this percolation configuration intersects one of the connected components an odd number of times, then clearly the conditional expectation is 0. And if it intersects if every connected component intersects an even number of times, then this is identically going to be equal to 1, almost surely, right? Because, well, suppose that this was connected. We're taking the product of these two spins, but since it's connected, we know that almost surely the spins are going to be the same. And therefore, yeah, it's identically equal to 1. Okay? So this is really one of the key advantages of this Fortuyn-Castellijn coupling. So this is again, it's a theorem due to Fortuyn-Castellijn. And of course we have the following corollary. Well, this correlation function is non-negative. Why is it non-negative? Well, it's the probability of some event of another measure. And in fact, corollary, if I take, so actually this event, this is usually we just write sigma A. If I take the product of sigma A and sigma B, this is going to be bigger than mu of sigma A times mu and sigma B. So of course, why is this the case? Those functions are not increasing functions. So it's clearly not going to be the FKG inequality for the Ising model, because this is not increasing. But this is equal to mu of sigma A symmetric difference B. Right? Because if we do the same spin twice, we just get always 1. This is equal to mu of the event F A delta B. Now, in fact, this event is increasing. Okay, actually, we don't use it yet. But if a percolation configuration intersects A an even number of times and B also an even number of times, then it will also intersect the symmetric difference an even number of times, right? So this event, this is a subset. Okay, it contains the event FA intersection FB, and therefore we have and now those two events are both increasing, and we have the FKG inequality for the percolation model. And therefore this is greater or equal than, well, mu FA mu FB. And this is equal to the desired thing. Okay. So those inequalities are called Griffith's inequalities. Okay. So I mean, the key idea here is that in principle, we have the FKG inequality for the Ising model. But in fact, okay, later we shall see we also need other inequalities, and those other inequalities are not FKG inequalities for the Ising model, but we still get them via FKG inequalities. So you can really do a lot using FKG inequalities. And now I want to write down a important consequence, which is not immediately obvious, but which is in fact very easy to derive from this. So what is it? This function satisfies FKG lattice condition. Okay. So I'm not saying it's at this point obvious that this is true or important. But I'm just saying, okay, before we were considering sort of, we gave a weight to every configuration and we proved the FKG lattice condition there. But now I have something completely different. I vary the coupling constants. And I have FKG lattice condition in the coupling constants. Right? So, okay, it's just a definition, it's just a statement. So in fact, why is this true? So what is the definition of Zj, right? I mean, here we define this Z, it depended implicitly on J. So it's the sum over all sigma of the product e to the j xy sigma x sigma y. But in fact, with this definition in hand, you can also write down relations between partition functions. So for example, if I want to look at Zj plus k, this is just going to be Zj times the expectation in the J Ising model of product xy e k xy sigma x sigma k y. So are there any questions up to, yeah?
Sorry, maybe this is a dumb question, but should that theorem that you have on the left be obvious when you don't just have a single connected component? So I see why it's true if you just have a single connected component in A, because then all expands out to a line. But what if you have multiple connected components that just intersect an even number of times? Then they may not agree. So why do you just get mu of FA?
Basically what you say is that if I have this set A, and suppose now I pick a vertex in this set A. Now of course you may contribute both positive and negative here, which is what you want to avoid. But now I know that this vertex actually is kind of paired with another vertex. And either they're +1 or -1 at the same time, but they're never different. Now if each vertex is coupled to other vertices in such a way that the total is even, right? So if every vertex is coupled to an odd number of different vertices, then they're always minus or plus together. Moreover, what you see is that yeah, sorry, does this answer your question or not?
Maybe I don't understand what you mean by intersecting an even number.
Yeah.
But it sounds like your condition, this even number condition just implies that all the spins have to align inside A.
Yes. So okay, let me just try to define it because yeah. So suppose, for example, this is the set A. Then this is a realization of f of A. Because if I pick a vertex in A, it may contribute positive and negative. But because those two are connected, I know that their spin is always the same. So I'm certain that they always contribute +1 in total. Now, if the set A was this, this would no longer be the case, right? Because this vertex is intersected, it's not coupled to other vertices. It belongs to A, but its connected component is just this vertex, so it really behaves independently of the rest, and now it kind of, you have the flip symmetry, which gives you a conditional expectation of 0. In fact, if A, of course, if A is odd itself, then you can never have this event f of A, right? Because there's always a connected component intersecting an odd number of vertices of A. And it's in fact easy to see that this expectation is 0 because you can just flip all the signs at the same time. All the signs in the Ising model. And that way it's easy to see that this is only non-zero if A is even, if it contains an even number of vertices.
Are we claiming FA is increasing?
Sorry?
Are we claiming is FA increasing?
FA is increasing. So let's go back to the original example. Let's do it like this. So in this case, FA is not realized, right? Because this component behaves independently of this component. I could replace this by a minus. But if I connect them, if I add an extra edge, then the parity becomes 2. And now supposing that all the parities are 2, if I add more edges, I'm kind of only joining things. So if your parity was 2 and then I add an even number to it, it's still going to be 2, right? So for example, yeah. I mean, this is not at all completely a trivial observation that this event is increasing.
Do you need to first suppose both A and B only contains even number of vertices? Otherwise, it is 0.
So here we're looking at this inequality, right? So you say if A and B,
Do you mean that A and B contains even number of vertices?
So here we're looking at the parity condition for A.
I mean, if A is odd, then your correlation is 0.
Yes.
Both sides are 0.
So I can give a very simple example to see this inequality. Suppose that A and B are the same set. Then here this condition is automatically verified because we're just looking at, our set is empty, and therefore this parity condition is trivial. But here we're really looking at the event that this set, which is the same in both cases, satisfies this parity condition. So maybe I can do a quick drawing. Yeah. So for example, in this case, if this is A and this is B, then we see that the parity condition is satisfied for both sets. And it's also satisfied for the symmetric difference, which is just a union. Okay? But now suppose, for example, that we look at this configuration. So in this case, FA is not realized, because this connected component only contains one vertex in A. But for the union of A and B, it is now satisfied. And so in this particular case, we see that this event is realized, but this event is not realized. So I mean, okay, I think we all agree that proof by example is not a good proof. But yeah, I'm going to leave this for the moment, and we can discuss this after. Yeah, so you can relate different coupling constants like this. And now, of course, when you are here, I really don't want to like do all the maths on the board, but basically what you can do is that you can expand the exponentials. So if you expand the exponentials, you will get positive prefactors with observables like this, right? So you get products of spins, and then you get the prefactors, but the prefactors are all positive. And essentially, because the prefactors are positive, we can use this FKG, well, it's Griffith's inequality, right? But it came from this FKG inequality. And it allows us to prove this FKG lattice condition. And in fact, and it's increasing in J. Actually, to see that it's increasing in J is quite simple, because there we can really use that this, I mean, to see that it's increasing in J, we just need to see that this is bigger than 1. To see that this is bigger than 1, we expand all the exponentials. We get a term which is just 1. Well, that's good. We just need to show that the other terms are non-negative, but they are non-negative because of the first Griffith's inequality. Yeah. So actually, in the context of height functions, we will later see that there is a certain measure where the partition function of the Ising model shows up as a weight. So you can see that actually now it's a partition function, it doesn't play a role in the random structure, but it's the weight of, well, it's part of a product of weights that in the end allows us to prove the FKG inequality for another object. So this is why this is an important inequality. Okay. So what I want to do next for today is to prove a number of, okay, at least state a number of abstract results when you put those measures with FKG inequality on an infinite volume space, like how can you get certain limits. And then I want to explain the Burton-Keane argument and quickly restate the non-coexistence theorem. And then I think we're going to leave the rest for next week, but we'll see how we'll do with time. So what you can also do is that you can take the Ising model on an infinite graph. So now, for simplicity, we take it maybe to be the square lattice. And again, we consider finite domains of C2. And the measure that we're going to consider, so let's call it the Ising minus measure within the domain lambda. We define it such that the probability that sigma is equal to sigma tilde. For this we want that, so it's 1 over z, the indicator that sigma on the complement equals -1. And then we have the product over the edges of E, yeah, let's just call it beta in this case, sigma x, sigma y. So again, this measure satisfies FKG inequality because it's composed of factors which separately satisfy the FKG lattice condition. Right? Also, for example, this indicator clearly satisfies the FKG lattice condition. But now we can do something cool, which is called comparison of domains. So if lambda is a subset of delta, then mu of lambda is stochastically dominated by mu of delta. So the proof is very, very simple because mu lambda, I mean, what we're here doing is we say, okay, we have some domain lambda, so this is lambda, and outside of this domain, everything is negative. And then we replace lambda by a bigger domain. So now if we have a bigger domain, clearly we get the smaller domain by just conditioning on an event. So this is just the event that sigma, sorry?
This stochastic domination has to happen when you have both minus boundary data.
Yes, yeah. It's really specific to having minus boundary conditions. Yes, this is very important. Thank you. Wait. So if I look at the measure mu of lambda, this is just equal to mu of delta, but conditioned on the event that it's -1 on the complement of lambda. Okay? But that is just the measure mu of delta conditioned on a negative event, a decreasing event. And by the FKG lattice condition, we immediately have the stochastic domination. Now for numbers, we know that if you have a decreasing sequence of numbers, you tend to a limit. And it's the same for measures. If you have a decreasing sequence or an increasing sequence of measures, you have stochastically increasing, then automatically you're going to tend to some limit. Okay, maybe you need to satisfy some tightness constraint, but in this case the tightness constraint is clear because the spin take values in plus or minus 1. Yeah. So we now consider a family of measures which are indexed by domains, right? So I just want to state things a little bit abstractly. Of course, in this case, we can think about the icing measure, but we can also later work with this height function measure, right? Because in this height function measure, we also define the height function in a domain. And we consider, so we define the following properties. So they're measures on R to the V. Right, so in this case, okay, it's R to the V, but in this case it's just plus or minus 1 to the V. So we define monotonicity in domains. So we call so it's called monotone in the domain if lambda subset of delta implies mu of lambda stochastically dominated by mu of delta. We call it tight if for all x in V, well, it's just a normal tightness constraint. It's a bit tedious to write down. Right? So it just means if I pick any vertex, I mean, okay, I know I'm stochastically decreasing, but I don't want to sort of fly away to infinity. So I'm just asking that for every vertex. If I make k very large, then no matter where I take the boundary, I'm going to be between minus k and plus k with a good probability. Then we define the boundary Markov property. So what is the boundary Markov property? Suppose that lambda, so if lambda has several connected components, then yeah, basically mu lambda is just a product over those connected components. Okay? So what I'm trying to express here, for example, in the icing model, if lambda is this set, right, the two parts don't interact, I just get independent measures in the two sets. Okay, I'm slightly cheating here because, I mean, both are already defined on this space, but let's just define them on the holes. And we have total independence. And finally, what is the fourth property? So it's a shift invariance. I mean, what does shift invariant means? It just means in this whole definition of the Ising model, for example, or in the height function, we didn't define the model differently in different places. So if I shift my domain 10 to the right, it's just like moving the function 10 to the right, but nothing else. So it kind of, yeah. So for example, mu theta of lambda, this is mu of lambda, but each configuration shifted. Are there any questions about these definitions? So one thing that I want to stress is that there are models which don't have the Markov property. So for example, you can think about FK percolation. Before we saw that if you have FK percolation, you have this factor 2 to the number connected of components. So this doesn't satisfy the Markov property, but under certain boundary conditions, it satisfies this weaker thing, right? I mean, here we're really saying we impose boundary conditions in a specific way because we impose the boundary conditions outside of lambda. So even, it's really a sort of weaker form of this, of Markov property. But yeah, I don't know if this is really important, but just a side note. Okay, so consider a family mu so now we're gonna write down some limits. So if monotone plus tight, then you can make sense of the limit. Okay. So basically the stochastic domination allows you to sort of take a limit, but then to avoid that the minus infinity case or the plus infinity case, you want the tightness. In the case of Ising model, this is completely obvious, right? Because the state space is bounded. Okay. So if you have monotone plus tight plus shift invariant, then also the limit is going to be shift invariant, because basically what happens is that, what's kind of interesting here is that if you tend to a limit, it doesn't depend on how you take your domains. So for example, if your model has a symmetry, if your graph has a symmetry, then this limit is going to preserve this symmetry. Because for example, suppose I want to show it's invariant under shifting it to the right by 1, right? So then I can say, well, first I take the limit along some sequence lambda n. So I do it like that. And then I just also take the limit along the sequence lambda n, but shift it to the right by 1. I shift all the things. So I know that the two things tend to the same limit, right? I can sort of intertwine the sequences and I know I still tend to a limit, so both objects tend to the same limit. And therefore this limit always preserves the symmetries. So clearly, in this case, you're also going to preserve the symmetry. And in fact, so this is going to be shift invariant, but if we also add this boundary Markov property, then you're going to be ergodic. So a measure on, in this case, RV is called ergodic if it is shift invariant and satisfies a 0-1 law on shift invariant events. Okay. So I have a detailed proof of this in the notes. I just want to quickly explain the proof. Suppose that this limit is not ergodic, then you're correlated with what happens locally in your system. So you have a shift invariant event. It can be something like there exists an infinite cluster, right? If you have an infinite cluster and you shift the configuration, it's still going to be there. So an event like there exists an infinite cluster correlates with what happens locally in your system. But now we argue that in fact over very long distances, things are independent in your system. Now, what that means is that I can define some event A here. So this is A, maybe it's A0, and then here I can define an event A1, and A2, etc. And now I have two inputs. First, if I make the distance between those boxes very large, then this boundary Markov property and the convergence, etc., tells me that those events are independent. So in the limit, this thing converges to independent Bernoulli random variables. On the other hand, I have some event which is shift invariant. So like let's call this event I. And maybe mu of I, okay, maybe it's something like 1/2. But in any case, it's going to be a fixed event with a fixed probability. Now, if I have independent Bernoulli random variables, what I said was that actually this event, by definition of changing the law, this is positively correlated with what happens in A0. So if I have some local event here, it really correlates positively with I. But now if I have a sequence of Bernoulli random variables and I condition on an event of probability 1/2, I cannot change the probability of all those Bernoulli random variables at the same time, right? Because the Bernoulli random variables are independent. If I have an infinite, if I have a long sequence of ID Bernoulli random variables and I want to change them, I really need to condition on an event with a very, very small probability. Okay? So independence, or rather asymptotic independence of Bernoullis contradicts I can change all their expectations at once by conditioning on a probability 1/2 event. Okay? So it really tells you, okay, well, you have decorrelation over long distances and therefore there's independence. If you're not ergodic, you find an event which is correlated with independent things, but this is impossible. So are there any questions about this particular proof? Finally, I want to point out that the FKG inequality is also preserved by taking limits. So if you take a limit of things with FKG, it also has FKG. I mean, yeah. For the purpose of this course, this is a result which is kind of trivial, but if you really want to prove it rigorously in all the generality of the world, then you need something which is called Strassens theorem, and this allows you to extend it. But for the purpose of our course, this is really just simple to prove. Okay. So I mean, okay, for Ising model, we have monotonicity. This is what we proved, just because to get your measure in a smaller domain, you condition on a decreasing event or an increasing event. So we have tightness because the state space is tight, so we get the limit. Shift invariance is baked into the model, and so is the Markov property. And therefore we get that the limit is ergodic. And the limit also satisfies the FKG inequality. So this gives us quite some useful tools to work with. Okay. So the last thing I want to present today is the Burton-Keen argument. So last time what we did was we saw this phase non-coexistence theorem, and this is one of the geometric inputs that we use. And the other geometric input is called the Burton-Keen argument. So the Burton-Keen argument is really non-two-dimensional. So it's not a 2D argument. And actually it does not rely on FKG. But it relies on finite energy. Okay. So what does Burton-Keen argument say? Let mu be a ergodic measure on percolation configurations of the square lattice graph. So G equals VE equals ZD in the corresponding edge set. with finite energy. And finite energy means the following. Suppose I take some box lambda, so for all boxes lambda, if A is an event depending only on lambda complement, then if A has a positive probability, then the following event also has probability. The intersection of A with the event at omega restricted to lambda is identically equal to 1. Okay. So I have some event A. To see if it's realized, I'm only allowed to inspect what happens outside of lambda. Right? So it really doesn't depend on what happens inside. And now I say that the measure has finite energy if for any lambda, if A has positive probability, then it also has positive probability that A occurs. But everything in this box is open. So then what is the conclusion? The conclusion is that the number of infinite connected components is 0 or 1. Okay? So you can ask how many connected components does this percolation have? I have a random subgraph induced by the open sites in this case. And I claim that the number of connected components is 0 or 1. Of course, this number is constant because we are ergodic. Right? So the ergodicity is an important input. And of course, in this theorem, we don't use FKG, but of course we use it implicitly because we use the FKG all the time to arrive at the ergodicity. Right? So implicitly, of course, it does play a role. So by ergodicity, okay, let's call capital N the number of connected components. And we already know it's constant, so okay, we don't have to pretend it's a random variable. And we want to avoid that N is infinity, and we also want to avoid that it's finite, but bigger than 1. So N is defined number of infinite connected components. Ergodicity implies N is almost surely constant. Okay. So first, step 1, assume that N belongs to the interval 1, infinity, and we want to derive a contradiction. Okay? Now suppose that N is 5. So there are 5 infinite connected components. Those are 5. Then the following event has a positive probability. It's the event that I take a very large box and all of my infinite clusters intersect the box. Right, so I take lambda. So then, for lambda sufficiently large, the event A, all infinite connected components intersect lambda, has positive probability. Now, of course, this event, okay, I defined it very badly, but it's almost measurable with respect to the complement of lambda, right? I could also say they intersect a neighbor of lambda, so let's do that. So I look if the connected components, if they reach to lambda, but to see if this event is realized, I don't need to know what happens in lambda. So in fact, A works the event A and lambda, they work very well with this finite energy condition. Because if A has positive probability, then the event that A occurs and also all of the vertices are open also has positive probability. But then if I chose lambda such that everything in lambda is connected to each other, it just means there's one infinite connected component. So then by choosing lambda wisely, this means probability there exists a unique infinite connected component is bigger than 0. But this of course contradicts ergodicity. So it's kind of funny because it means that it's very much a qualitative argument, right? Because, okay, what did I want to say? Yeah, I mean, it's qualitative because we don't really know how big lambda should be before it intersects everything, etc. Yeah, I mean, when you do the ergodicity somehow, like, yeah, maybe you could push everything through all of the arguments. I didn't think about it too much, but these are really the steps in the argument where you kind of lose the quantitative control. Yeah. So now, of course, there's the question, what happens when n is infinite? And we need to do something different. So if n is infinite, then we're not going to look at this event, but we're going to look at a slightly different event. Namely, we're going to make lambda so large that at least 3 infinite connected components intersect the box. So let's say, let's call it A prime. So A prime is the event at least 3 infinite connected components intersect the neighbor of lambda, right? So I have my box, I have 3 infinite components which intersect it, but there may also be other ones. Now, of course, in this case, A prime is not measurable with respect to what happens outside. Because, for example, if everything in lambda is connected, then this event can never occur. But now we can slightly change our definition, namely the following. We define A as the event that at least 3 infinite connected components for omega minus lambda intersect the boundary, right? So now I don't consider my configuration, but I consider my configuration, but I just remove all the vertices which are in lambda, and now I look if I have 3 infinite connected components. Now, of course, this event is obviously measurable with respect to what happens outside of lambda. Okay? Right. So if n is infinity, then by choosing lambda wisely, this event has a positive probability. And by finite energy, we also know that this event and everything in lambda is open also has positive probability. But this means that I have a sort of box where three infinite connected components come together, right? So they really need the box to be connected. Now, I claim that this is a contradiction. So we say that lambda is a trifurcation box if a lambda occurs, right? So, okay, now we just call this event a lambda. And all sides which belong to lambda are open. Now, we know that trifurcation boxes exist. That means they occur with a positive probability by assumption, right? So we assumed that we have those three infinite components. We chose lambda big, we have finite energy, so this occurs. But what does this mean? I mean, it means we have the shift invariance. So if we know that it happens with a positive probability, and we have the shift invariance, we also know that they happen with a positive density. Okay, of course not all of them will occur, right? So maybe here we have a bad one, that's not a trifurcation box. But we know that this probability, so they occur with density epsilon bigger than 0 by assumption. Okay, so we chose lambda. We covered our space by boxes like this. And this epsilon density is fixed, right? It's just a probability that this is a trifurcation box, and therefore the density of trifurcation boxes. So now if I look in a super big ball surrounding the origin, so maybe this is a ball of radius capital R, then the number of trifurcation boxes is going to be, well, roughly R to the D times epsilon. Right? I have a density of epsilon, and the mass of the volume of my ball is R to the D. But by definition of a trifurcation box, these trifurcation boxes behave like a sort of tree. So the boxes, they are the vertices. They all have degree 3 or higher. They can connect to each other, or they can kind of point out of the boundary of this box. Okay? But if we have a tree where every degree is 3 or higher, which is a finite tree, okay, let's say all the interior vertices have a degree of 3 or higher, then the number of leaves is at least the number of vertices, right? So the number of leaves it must therefore also exceed R to the D times epsilon with a good probability. But this is in fact impossible because each leaf corresponds to an arm of this cluster pointing out of the boundary. Right? So, of course, the boundary grows as R to the D minus 1. Okay? So it's really a geometric argument which relies on the amenability of the group. Okay? Like we work on a group where we can find balls such that the volume of the ball grows faster than its boundary. And yeah, so this works in any dimension, but in much greater generality as well. Okay, so this together with the non-coexistence theorem presented last week provides the main input for the delocalization, and I think we're going to spend a good part of next week doing that. Thank you.